Welcome to the Fundamental Theorem of Arithmetic. This section reveals one of the most elegant facts in all of mathematics. Take any collection of prime numbers, say 2, 3, 7, 11, and 23. If we multiply some or all of them, allowing repetition, we get many composite numbers. For example, 7 times 11 times 23 equals 1771. And 3 times 7 times 11 times 23 equals 5,313. 2 times 3 times 7 times 11 times 23 equals 10,626. We can also use repeated primes like 2 cubed times 3 times 7 cubed equals 8,232, and 2 squared times 3 times 7 times 11 times 23 equals 21,252. We can produce infinitely many numbers this way. But can we produce every composite number? Let us factorize the number 32,760 step by step. We divide by the smallest prime, which is 2. 16,380 is still divisible by 2. 8,190 is still even, so we divide by 2 once more. 4,095 is not divisible by 2. We move to the next prime, which is 3. 1365 is also divisible by 3 by 3. 455 divided by 5 gives 91. 91 equals 7 times 13. Both 7 and 13 are prime. We have reached the leaves. Collecting all the prime leaves gives us 2 cubed times 3 squared times 5 times 13. They shall 5 times 13. Every step in the tree was forced. No choice was ever available. This is why the factorization is unique. This observation leads us to the fundamental theorem of arithmetic. Every composite number can be expressed as a product of primes, and this factorization is unique, apart from the order of the factors. This is called the fundamental theorem of arithmetic because of its basic and crucial importance to the study of integers. Let us see what order does not matter means. 30 can be written as 2 times 3 times 5, or as 3 times 5 times 2, or as 5 times 2 times 3b. These all represent the same factorization. The primes used and their counts are identical. Let us see uniqueness in action with the number 210. We can write 210 as 2 times 3 times 5 times 7, or as 7 times 2 times 5 times 3, or as 5 times 7 times 3 times 2. These all look different on the surface, but each uses the primes 2, 3, 5, and 7 exactly once. There is only one factorization into primes up to the order of writing. The fundamental theorem guarantees this for every composite number. An equivalent version of this theorem was first recorded by Euclid. It appeared as Proposition 14 of Book 9 in Euclid's Elements. However, the first correct proof was given by Carl Friedrich Gauss in his Disquisitiones Arithmeticae. Gauss is often called the Prince of Mathematicians. He is considered one of the 3 greatest mathematicians of all time, along with Archimedes and Newton. In general, given a composite number x, we write it as a product of primes. The primes are written in ascending order, so P1 is less than or equal to P2, and so on. When we group identical primes together, we get powers of primes. This is the compact or canonical form. For example, 32,760, written out as a long product, has 3 2s, 2 3s, a 5, a 7, and a 13. Grouping the repeated primes gives 2 cubed times 3 squared times 5 times 7 times 13. Once we fix the ascending order, This representation is completely unique. To summarize, the fundamental theorem of arithmetic guarantees that every composite number has a unique prime factorization. Primes are the indivisible atoms of arithmetic. Every composite number is built from primes in exactly one way. In the next sections, we will use this theorem to compute HCF and LCM and to explore further properties of numbers.